Welcome back, students. Um, I hope that you all had a safe experience uh, with Hurricane Matthew. At my house, we held out okay. Anybody, raise your hand if you're from Flagler or Volusia County. And are you guys, because you guys got hit the hardest, I think. Raise your hand if you stayed in the dorms, or actually, you live in the dorms, but then they force you to go into another building. Raise your hand if you had to do that. Nobody? So nobody here stayed on campus? Raise your hand if you stayed on campus for the. Okay, what about you?
I went to my brother's apartment.
So you didn't stay on campus? Okay.
Well, it's on campus.
Oh, in the towers, you mean?
Ninth Circle.
Okay. All right. I guess they're doing things differently. Now, I know that a lot of you are not only wondering about what a polar bear is doing on snowshoes, but you're probably wondering about exam 2. We're going to do exam 2 on schedule Thursday. It's going to be, as always, in lecture hall here, 50 points. And we'll be covering topics from L9 to L15. That's this lecture. There is no lecture 14, though, because that was canceled last Thursday. And we're still pretty close to the pace that I want to be on, so we're doing okay. Being as how the lecture or the exam is going to cover these lectures from L9 to L15, you're basically talking chapter 4, chapter 5, the mini blurb I did on universal gravitation in lecture, and last Tuesday's special lecture on hurricanes and atmospheric pressure, which is slightly different approach than the textbook, although chapter 6 concepts on pressure and the kinetic theory of gas were kind of embedded and talked about in last Tuesday's lecture. Because we did talk about atmospheric pressure. We had a little tiny homework about it. You're going to have some homework tonight, and I'm going to give you probably a tiny homework and then a little bit bigger review homework, kind of like we did for exam 1. And anyway, so then as much of chapter 6 as we cover today. Now it's going to be, we're going to be doing a little bit of hopscotch in chapter 6, but today's lecture is in chapter 6. Take down the page references as we go through lecture today, and that'll be helpful for you. I'm going to have a question and answer session on exam 2 at the end of lecture today, so before we dismiss. So I'll go over some more of this at the end of class. Another thing to get you ready is the SI review session. And that is going to be today, this afternoon, Classroom Building 1. So this is Classroom Building 2 where we are right now. Classroom Building 1's across the way. And you're going to be on the first floor, room 122, 3 o'clock to 4:30. Now, if you can only make it from 4 to 4:30, just go. If you can only go from 3 o'clock to 3:25, go. Just go and, learn and reinforce different concepts with Maria. Also, past SI online sessions, which are Wednesdays. So oh boy, did they have, did anybody participate in the online session last Wednesday? Nobody? Anyways, those are now recorded. You can review them The SI schedule page has the links for the recordings. I use these with my online, my W section of Physical Science 1121. So it works really good. Now you're not going to be participating in the office hours, but you'll be able to look at everything that they looked at, and you'll hear them talking or texting. Some people don't have microphones and stuff, but and if you're wondering, yeah, the SI schedule page looks like this, and then let me just blow it up here. Right here it says click for recordings. If you click that, it'll take you down to the bottom of the page, and that's where the list of recordings is. So I've got the links to every one that she has done, all the Wednesday afternoons, the late Wednesday online sessions, and hopefully that'll be helpful for you. Okay, let's keep going and talking about heat energy. This is a picture from Florida, actually. I'm not really sure exactly where. I bet if you looked at those street signs, you could figure it out, if you could blow them up and stuff. That is a convection, that's a thunderstorm, it's a supercell. And it is a huge convection system, and convection occurs because of the differential heating of the atmosphere that carries a lot of water vapor. And, you know, this diagram from page 93 is the core of what we're going to be talking today. This idea of a phase transition from gas to liquid, liquid to solid, solid to gas, or vice versa, gas to solid, solid to liquid, liquid to gas. All those phase transitions are important for any number of physical phenomena, one of which was Hurricane Matthew. The whole reason that we missed lecture 14 on Thursday was that we were trying to get ready for this huge water-dominated system called Hurricane Matthew, an ocean atmosphere storm that caused trouble to us specifically because of the heat energy that is deposited from the sun, Cody, at the rate of 1,061 watts per square meter into the ocean. And then the ocean currents move, and the atmospheric the atmosphere over the Saudi Arabian peninsula. They develop pressure waves. They propagate across the Sahara, across North Africa, and then when they hit the Atlantic off the coast of West Africa, bam, they interact with that heat energy in the ocean, and they turn into this big, frequently, at this time of year, these big atmospheric storms. So that's the interaction between gas and liquid, and all the energy considerations and pressure considerations, Claudia, between those two states for water. It's mainly water that we're talking about. And water's the primary actor. But, you know, it's not the only thing. This diagram, there's other things than hurricanes to worry about that you need to understand these kind of phase transitions. Another example, we currently have this dream, and people are trying to work on it, of colonizing the moon and colonizing Mars. And there's been buku movies, science fiction movies, but hopefully by the time you guys are old and cranky and going around saying, you little young whippersnappers, when I was a kid, they only went, you'll be up there and your kids might be going and living on the moon or on Mars. maybe one or two of you guys. If you become a billionaire or something like that. You can buy your own rocket, I guess. Maybe eventually. So those guys, so here's a picture of them testing out the Mars rover. Notice anything about this picture? There's grass. The sky is blue, so this is Earth. Matter of fact, they do a lot of the testing for Mars equipment and spacesuits and stuff and moon landing equipment out in Arizona. They do it up in Hawaii and stuff. As I understand, they did it up in the Apollo astronauts also worked up in Iceland on some of the lava flows up there in Iceland. But here they are looking at, rocks down in Arizona. Here's one of the vehicles that they're trying to develop. And, all of that stuff, those spacesuits, the transporters, and even the probes that are up there now, the satellites that we've got orbiting and the landers that we've landed, they're looking around for evidence. You know what the biggest thing on their list is water, H2O. And the reason that they're focused on that is because we want to colonize, if we can, and we need water. You know what? We can make oxygen from water. There's plenty of I shouldn't say plenty, but there's enough solar energy to break water down into oxygen and hydrogen if we can get to Mars and we can get to water. Same thing on the moon. They found that they're pretty sure that on the moon, in some of the craters on the north pole of the moon and the south pole, so top and bottom, where in the deep craters, kind of in the corner, in the crevices, they think there's a lot of water ice because it's so deep in those crevices and crevasses that the sun never gets there to melt them. Now, if you're around the equator of the moon, the sun is blazing. Water's gonna, if a meteorite, if an asteroid or if a comet impacts the moon of any size and releases water, it carries water into the moon and deposits water, and some of it is accumulated on the moon by gravitational attraction. At the equator of the moon, it's going to evaporate like that. It's going to go off into space because the moon has no atmosphere. The sun is very intense, and if you put a piece of ice on the surface of the MOON, it would turn into water vapor and just disperse into space very easily in the sunlight at the equator. Now, up at the poles, the north and south pole, in some of the crevices and the deep craters, they think they still have water. Because if you're in shadow on the moon, it's cold. It's free. You freeze your you-know-what off, okay? Because it's basically like being in outer space. But if you're in this outer space and you're getting direct sunlight, at this distance from the sun, the moon and the Earth are just about 93 million miles away from the sun, and it'll get hot up there. The astronauts up in orbit, they have to protect themselves from solar heat gain as well. Anyways, we want to know all about water on different planets. We even have a special satellite up in space called Kepler that is now defunct. It ran out of electrical power, but it has been mapping nearby stars in a certain region of space to look for planets. And what we're really looking for are planets about the size of Earth and about the same distance from the sun, from their star. And we're especially concerned about the presence of water. Now, this is the Mars Reconnaissance Orbit. This thing's been up there working for years. Great observatory. It's got radar. It's got optical. It's got infrared. detectors, big solar panels, as you can see. It beams a lot of energy back. I believe it also interacts with the landers down there that are on the surface. You know, they relay data up to this baby. And then this orbiter relays it back to Earth for them. But here's a picture of the Mars Reconnaissance Orbiter, or this is what they call an artist's concept, artist's conception of Mars Reconnaissance Orbiter, MRO, orbiting over, the ice cap, the polar ice cap of Mars. You know, and go ahead and make a note, Mars Reconnaissance Orbiter. You should be taking notes on everything I'm saying right now, actually. Mars Reconnaissance Orbiter has radar, and it is ground-penetrating radar. So we can penetrate a certain depth of the surface of Mars, and what we have found is that there's beaucoup, or excuse my French, there is a ton of water ice under the surface of Mars. Not liquid, but water ice under the surface. It's like all this, there's a lot of ice, and then it's covered over with a lot of dirt. Kind of like up in Alaska. You know, the permafrost up there in Alaska, the land of the midnight sun. There's a lot of water in the ice there, and it only melts, like a few days of the year in the middle of the summer, maybe, if it's a good day. Okay, this ground-penetrating radar, when we first developed it? Back in the 1960s. We put it on, they've got it on Mars Reconnaissance Orbiter now, but back in the 60s, the U.S. government put a satellite with ground-penetrating radar to look at Soviet missile silos, so they can really read the Soviets can't, the Russians cannot hide their missiles from the good old U.S. And they famously published back in the late 60s or early 70s a photographic or a radar study of Egypt, where they examined with this satellite the buried Egyptian waterways and canals that were built by the ancient Egyptians and are now buried by, tons of sand and stuff, but they could still see it all. So they published this study in National Geographic, The Wonders of Egypt, from space. But the reason they did that was to tell the Russians, yeah, we got it. We got you. Don't be trying any funny stuff. We know exactly how many missiles you got and where they are. And of course, they can do the same thing. So it actually makes things safer, so nobody gets tricked. Here's something that the Mars Reconnaissance Orbiter has found. See that valley? And it looks like snow. This is a false color image, so that's not snow. But the dark brown strips there in the lower left corner is actually signs of liquid water that flowed days ago. When this set of data was taken near the Hale Crater complex, it was days, weeks, months old. In other words, it wasn't a million years old like rocks. I mean, we can see rocks that were formed in water a million years ago, but these ones were formed a very short time scale. So, in other words, seasonal flow of water. So we want to know all about that. And guess what? Why does water flow sometimes and sometimes it doesn't? Phase transition from solid to liquid. And here's where that particular crater complex is. So when you look at the disk of Mars and you see the canals, this thing, they used to think this was a set of canals, but it's really this gigantic canyon. Like the Grand Canyon of Earth would fit, about 7 Grand Canyons would fit into this thing. It's ginormous. They have the biggest volcano in the solar system on Mars. It's kind of a cool place. Anyway, so this little place down here where they saw those water streaks from water, the sign of flowing water was down here in the Hale Crater Complex, southern hemisphere of Mars. In this picture, you can't really see they didn't optimize it for the polar ice caps, but actually up here in the north and down here in the south, if you're looking, if the time of the year is right, you'll see a polar ice cap. And side comment, the polar ice caps of Mars are mostly CO2 ice. And in Chapter 6, I got a little blurb about CO2, CO2 ice, and CO2 gas. Now, here's another diagram from page 116, and this one is related to a brain burner that we're going to tackle next Tuesday, some calculations related to this. Now, I'm going to use this diagram today to give you some basic ideas about phase transitions. And this is a diagram that on the horizontal scale, the measurements labeled Q are in joules or calories of energy, and the vertical scale over here is a temperature scale in Ks or kelvins, and we'll talk about that in just a minute. Now, last time we were talking about the E pluribus unum principle in the context of atmospheric pressure. Now, what does that mean? Well, it means that if you look at a submicroscopic view of what molecules do, and this is completely theoretical. I mean, because we can't really see molecules. Well, we weren't able to for hundreds of years. We just recently, in the past 10, 15 years, have been able to see a few molecules, but they're very tiny, so we kind of envision them as little billiard balls recoiling with the boundary or the surface of a container, and every time a molecule bounces off the wall, it exchanges a little bit of momentum, a little bit of delta P. And that happens at such a fast rate that you get some net force. And if the container can pull back or hold it in, the gas will be contained. If the pressure gets too big, the balloon will pop. The container will not be able to hold it back, and that outward pressure will win. And bang, your balloon pops open, or whatever it is that you've got in your container. All right? High pressure is pretty dangerous. But this is I call this the E pluribus unum principle, because E pluribus unum means from many one, and that's really what we're doing. The pressure, so this is an important concept for you, E pluribus unum. Concept number one, pressure is a macroscopic measurement that encodes the recoil interactions of many, many, many submicroscopic collisions that we cannot see. So for many submicroscopic collisions that we cannot see, we derive one macroscopic measurement, the pressure of the gas or the pressure of the liquid. And last time we talked about atmospheric pressure. All right, now this is kind of an idealized picture from page 98, but it's a good one. It works well. And with this picture of basically like a little teeny BB or a billiard ball bouncing off a wall, yeah, we can figure out a lot of the pressure properties and temperature and volume and all that stuff for a gas. You know, it's kind of an idealized view of a gas. Now, I want to ask you an iClicker question, if you will. So take your clickers out. And I want you, we're on frequency AA, And you guys, I'm going to update your clicking points or your clicking tallies after exam 2 again. Okay, so you know kind of where you stand grade-wise after exam 2. I'm going to ask you a question, and I might ask something very, very similar to this on exam 2. So jot this question down in your notes as you think about it. Question 1. A dense gas, highly concentrated. Go ahead and vote. "20 seconds. And Darian is operating the machine, so she's not going to wait. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. She clicked before I got to 0. All right. Let's see. Can you give the histogram? Aha! You guys did pretty good. Okay. Answer is A. And for those of you that want to make this part of your notes, here's kind of the concept behind this answer. A dense gas, highly concentrated, has more recoil interactions per second as compared to a sparse gas. Why is that? Because a dense gas means more molecules. Okay? More molecules per cubic centimeter, for instance. And so you're going to get, for every square centimeter of surface area, you're going to get bombarded. It's kind of like, you know, like, here's another phrase that you could write down in your notes. A dense gas is like when it's raining cats and dogs. Versus a dilute or sparse gas is just kind of a drizzle. You know, you can walk through a drizzle and you're not going to get totally soaked. But if you're outside and it's coming down cats and dogs, even if you have to dash from garage H over to this building, you know, like about 30 feet or 40 feet, you're still going to get soaked to the skin if it's raining cats and dogs. So that's another way to think about it. Uh-oh, this slide is looped up. Well, my next slide, let me see if I can do something here. Where's my cursor? There we go. Let me see something here. All right, now I want to make a comment to you about this diagram that we just had. And this is a diagram from your textbook, a recoil. A little bit of delta P, and then minus delta P going off to the left. And if that delta P, or if, you know, a zillion delta P's end up moving that wall outward, then you can say that the gas, the collection of all those zillions of little molecules, has done some F delta X work. All right? So if the container expands, so go ahead and make a note of that. If the container expands, in other words, the wall moves a little bit, you can say that the gas has done some work. You've changed the volume by changing, you know, moving the surface outward by a millimeter or even a micron or a nanometer. You can say that some work has been done. And so students, work the energy content of a gas or a liquid or a solid, energy is also a macroscopic measure of many, many molecules aggregated dynamically to give you one macroscopic measurement. So that amount of work is encoded in something that we call temperature. The temperature is the macroscopic measurement by which we express changes in the average kinetic energy of objects in the gas. Now, there's a couple different temperature scales that we customarily use. Good old Fahrenheit. Professor von Fahrenheit, he developed the first one. And he said, all right, whoa, Dr. B. Anybody see my typo? I made a mistake here. How many degrees of separation should that be? Between boiling and freezing? No, for Fahrenheit it should be 180. So I'm going to have to change this for the second lecture. That should be 180 degrees of separation between freezing water and boiling water. In other words, from 32 up to 212. See how I was thinking 212 when I typed that sentence, but what I should have done is typed in 180. All right, now the next one, second customary scale is called Celsius. This is correct. 100 degrees of separation between water freezing point of water, and the boiling point of water. Okay? And you can see that on this diagram. The Fahrenheit scale is this little vertical thermometer on the far right. And you can see it's labeled, and this is a diagram from your page, from your textbook, page 104. And you can see them, I mean, they're all over the place. 212 up here for the boiling point of water, and over here on the middle thermometer, 100. That's the Celsius thermometer. Now down here on Celsius where water freezes, that's declared to be 0. Right? It's a metric system scale. Fahrenheit is not a metric system scale, so they're not working with hundreds between, but they have 180 degrees of separation between 32 degrees Fahrenheit for the freezing point of water and 212 degrees Fahrenheit for the boiling point of water. Now the third scale, and this is the one that we're going to use, is called the Kelvin scale or the absolute scale. The Kelvin scale was invented by a guy named Lord Kelvin. And the 0 point is what they define. Now, the Celsius scale has a 0 point defined based on the behavior of water, and the 100-degree point based on another behavior of water, the boiling point. But Kelvin scale is this theoretical point at which your gas or your liquid can't do any F delta X. It can't do any more F delta X work. You can't extract any work from the system at some basic temperature. All right? The way to cool things off is by extracting work. You know, your refrigerator at home, it extracts heat from the stuff in the refrigerator and expels it through the fan, you know, usually down at the bottom of the refrigerator, you know, where there's a little bit of warm air coming out. It does that constantly. Right? And that's how it works. You can't refrigerate anything. You can't actually get to absolute 0. That's down here in the Kelvin scale. But you can get really close, like 0.000001 and even colder on the Kelvin scale. Now, on the Celsius scale, it corresponds to negative 273 Kelvin. And on the Fahrenheit scale, about negative 459.67 on the Fahrenheit scale. Now, there's the other thing about the Kelvin scale is we still want to have 100 kelvins of separation between the freezing point and the boiling point of H2O. Right? So they basically take the standard Celsius scale and say, all right, I'm going to take all those 100 degrees, but I'm going to make the 0 point down at absolute zero instead of way up there at the freezing point of water. So the Kelvin scale is the scale that we're going to use most of the time. And just so you know, exam 2, I don't want you to worry about, Dr. B, do we have to convert Fahrenheit to Celsius? The answer to that is no. N-O, no, never. I hate making you guys do converting Celsius to Fahrenheit and vice versa. It's a pain in the burp. All right, but we are going to have to convert. We are going to have to go Celsius to Kelvin, and so basically it's either subtracting 273 to go from Kelvin to Celsius, or adding 273 to go from Celsius over to Kelvin. That's an easy conversion. But most of the time we're going to be doing Kelvin temperatures. And if you have a calculation, I'll be talking kelvins. And it'll be clear. I won't try to do any tricky questions with that. Okay, questions before we continue? Wow. That's amazing. I thought you were raising your hand, but your hair is, so long. It's way up here. That's cool. Very good. All right, let's keep going. Here's a picture of the SR-71 Blackbird, a plane I wish I could have, but it's the fastest plane ever made, they think. And, I've seen, it's a spy plane. They developed it back in the 60s to spy on the Russians. All the cool stuff is designed to keep an eye on the Ruskies. Anyways, the SR-71, it goes so fast that the leading edges, the front edges of the wings, glow red hot. And I know that because I saw one once. I was out in a beautiful August night, late after midnight, and I was looking up out in the middle of a soccer field and trying to watch the meteor showers, the Perseid meteor showers. And I was watching them. They were coming in pretty good. It was kind of cool. And all of a sudden, I saw this kind of a reddish thing go from the northwest all the way down to the southeast. So I'm laying out there, and I'm kind of drifting off to sleep and waking back up again. But I saw this thing. I thought, and it was kind of a V shape. And I thought, oh, cool. It's a flock of geese heading south for the winter. And they're so high up, they're catching the first rays of the sun. But it was way too early for that. And geese don't fly that high. And so I thought, that's what I thought. But then, an hour later or something like that, here it comes again from the southeast back to the northwest the way it came. I thought, oh my God, it's an alien. It's a UFO. So I'm in grad school, right? And the next day, I told my thesis advisor, my boss, I said, yeah, I saw a UFO last night. It was this thing. It was the red V-shaped object. It came from the northwest down to the southeast. And then an hour later, I saw it go from the southeast over to the northwest. UFO. It was cool, Dr. Hiscock. And he's giving me the eye like, yeah, kid, good, nice. Let's get back to work. Let's get back to reality. But then I was telling my buddies in grad school, and they said, you know what that was? That was probably the SR-71, because that summer they brought it out of mothballs. I don't know what they were supposed to be looking at. I think in that year it was somewhere over in the Balkans or something like that, Serbia or something. Anyways, they were training. And so we figured out what. So it was no longer a UFO, it was just a CFO, a cool flying object. But it gets red hot in the leading edges when they're at high speed. So let's talk about that. Now let's talk about calories. A calorie is a unit of energy, and it is thermally defined. And here's just the basic definition. The metric system, calorie, it's the amount of energy that you need to drop into a gram of water to raise it from 14.5 Celsius up to 15.5 Celsius. Okay, it's a certain amount of, if you inject more than that, the water will heat up a little bit more than 1 Celsius degree. Right? So that's the basic heat derived unit based on liquid water for the metric system. Now this diagram over here to the right is how this all was figured out back in the 1800s by a guy named James Prescott Joule. Very interesting guy. And what he figured out was, all right, if I operate this device, so take a look at this device. All right, you've got a container of water here. And in the container, you've got paddle wheels. This device, the paddle wheel has a vertical axis, so it'll spin kind of like a revolving door, and it'll stir up the water. You can measure the amount of kinetic energy by measuring the delta Y. So he would take a weight tied to a string over a pulley and then around another pulley, and when this weight fell, delta Y, it would cause those paddles to spin. All right? So that dumped a bunch of kinetic energy into the water, because eventually that weight's going to hit the floor. You know, after a certain amount of delta Y, it hits the floor, no more potential energy is converted into kinetic energy in the water. Also, the paddles will stop. So the water will have all the kinetic energy. And what James Prescott Joule said is, all right, I'm going to use this little thermometer. See this little thermometer over here? This is kind of an idealized schematic diagram. But he measured the change in the temperature there. Okay? And so here's how he did it. He got, you know, a certain weight, a certain number of centimeters. So over here, he knew how many joules or Newton meters of, see, it didn't get named the joule until after this guy did this experiment. As a matter of fact, the unit of energy is called the joule precisely because of this experiment. So anyways, he measured the energy over here, mechanical energy, mg delta Y. And then over here, the temperature. So he knows that a certain amount of kinetic energy went into the water, and it raised the temperature by a certain amount. And it turns out to be this ratio here. For every gram of water, 1 calorie raises the temperature of the water measured by the thermometer by 1 Celsius degree. All right, so here it is again. And so it could be a calorie from sunlight or that pulley device. And the way to encode that numerically is to say that for liquid water, it takes 1 calorie per gram per Kelvin, or 1 calorie per gram per Celsius degree. And that is a property of water. Now, solid water, which we know as, another typo here. This should be the word only. That's a fat finger error. Solid water, which we know as ice, It only takes 0.50 calories per gram per Kelvin. All right, so we define the calorie with a gram of liquid water at 14.5 Celsius. And solid water, you can heat up ice. I mean, if you have ice that's like at negative 10 below zero, it's really cold. It won't melt until you get it up to 32 degrees Fahrenheit. Okay, so you got to heat ice before you can melt it. And that's the amount of energy that it takes to raise the temperature of solid water. Now, what is the difference between liquid phase of H2O and its solid phase? That's what we're talking about, these phase transitions. Well, the temperature of the water is either above 273 or below it. All right? And 273 Kelvin. Now, that's the freezing point of water. And side note to yourself, you guys, that's 0 degrees Celsius, 32 degrees Fahrenheit. All right? At 273 Kelvin, 273 degrees above absolute zero, 273 Kelvin, water liquid and water solid can coexist perfectly. Right? That's the temperature of ice water. And a lot of scientists, you know, if you take a chemistry class, a lot of times they'll talk about an ice water bath to keep the standard, the temperature of their reaction contained. You know, they mix a bunch of chemicals in. They want to make sure they keep it at a certain temperature. A lot of times they do that with ice water. And they do it with other stuff, but ice water bath, yeah, because they'll both coexist if it's, you know, insulated well and stuff like that. Now, below 273, crystalline bonds can form. Those are intermolecular. So the H2O molecules bond to their neighbors, and they form a solid. You know, so for those of you that are in Florida, that's the stuff we call snow, S-N-O-W. Raise your hand. I'd like to see a show of hands, just for curiosity's sake. Raise your hand if you've never actually physically been in the presence of real snow, like from winter snow. If you've never been in the... That's a good number of you. It's pretty... I'd like to say it's pretty cool. It's actually kind of excellent. Yes? Dude, I used to live in Montana. It's been snowing since the end of July out there. It's great. Yeah. So, I mean, you know, Minnesota, it's crazy. You know, that doesn't surprise me. I lived in Minnesota. Where do you live? The cities? Yeah. Yeah. You go up to the Iron Range or something. It's, you know, it's already frozen. They already got the igloos built. But out in Montana, there's many, many Halloweens where it snows. So it's kind of crazy. Anyway, the intermolecular bonds are important, and they represent a lot of stored energy. It takes energy to force those bonds apart. When those bonds are forced apart and broken, the water goes from solid to liquid. Right? Now, the liquid, most substances can exist as a liquid. In a liquid state, there are still intermolecular forces, but they're really weak. So make a note of this. In the liquid state, intermolecular forces exist, but they're really weak. They're not strong enough to form a regular crystalline solid of any kind, but they do hold a small amount of water together in a droplet. Water drops in the atmosphere, raindrops, are held together by very weak intermolecular forces. And at a certain temperature, Those are the only things that will act. Now, there's another temperature, 373 Kelvin, and if the liquid water gets above that, all intermolecular bonds are broken, and now you have a gas where there's no bonding at all. Now, as I say here in item 3D, the energy that's stored is, you know what it's in a intermolecular bond? It's not gravitational potential energy, it's electrical. EPE, electrical potential energy. We'll be studying electric potential energy probably week after next, if I recall correctly. So electrical potential energy is in other words, between electron and proton, for instance, negative and a positive, they'll hold together if they're close enough, if they have a chance. And at the right temperature, they do, and it will form a crystalline solid like ice. Now, other substances you just have to look up in a table. And we're going to have a table in just a second here. So here's the thermal equivalent of heat. So a calorie of energy, so that's 1 gram of liquid water from 14.5 to 15.5 Celsius. Okay. That's the same as 4.184 joules of GPE, mg delta Y. Or 4.184 joules of solar energy, radiant energy, beaming in 93 million miles from the surface of the SUN into a droplet of water, or anything else. So a calorie, calorie is a kosher energy unit. It's perfectly fine. It's a metric unit. Joule is also a metric unit. Calorie is frequently used for thermodynamic applications. But sometimes joules are used, and you're perfectly well to use them. And my wonderful students, when we are working on these melting and freezing and boiling problems, we're going to be working in kelvins and calories and grams, because the calorie is defined with a gram, not a kilogram, right? Now, you can do everything with kilograms and joules and kelvins if you want, and many people do. So if you're a big industrial engineer, you're designing some big, huge chemical cauldron where you're cooking up a bunch of Jello molecules or MSG molecules or any kind of molecule in bulk, you're probably talking kilograms and joules and stuff. The food calorie, usually symbolized with a capital C, except on the actual nutrition facts on, whatever it is you're eating, Cheetos or Doritos or whatever. Those calories are 1,000 of these little thermal calories. So this one here, this is with a little c. You sometimes hear it called the gram calorie. In other words, the amount of energy to bring 1 gram up by a Celsius degree. The food calorie is 1,000 of those. Okay, a food calorie is also sometimes called a kcal. In other words, K for 1,000 and cal for this kind of calorie. So 1,000 thermal calories is a food calorie. You're going to have a problem tonight in your homework where you're going to have to compute some you better make a note of this, mg delta Y, gravitational potential energy or work, mg delta Y in joules, and you're going to have to convert it into food calories. So for instance, every time you do the stadium over at Bright House, you're going, 100 feet up in the air. That's a lot of vertical steps. That's a lot of mg delta y that you got to produce with your muscles. And you've got to do that from food, right? And so, so every trip doing a stadium, although as I understand it, you can't actually get into the stadium to do stadiums there, but you could do stairs, I guess, at the parking garage. Anyways, wherever you do stairs or stadiums, it takes calories to do it, and you're going to have a homework problem with that tonight. So just try to remember this when you're on that homework problem. All right, here's the table. Let's just take a look at this. This is from page 96. H2O. So there's the boiling point and the melting point. And hey, you guys, there's a typo in the first line. Density is a solid. That should be 0.92. So make sure you make a note. And this is a table from your textbook, page 96. So make sure you use 0.92 for that. And just look at this. Different melts. Every substance is different. Ethanol, the melting point is negative 114 Celsius. So ethanol, so a lot of people, they put vodka in the freezer and it won't freeze. It'll still be liquid. And that's because the melting point is so low. You got to get it really, really cold in order to actually melt, or in order to actually freeze it. But yet, here's the other interesting thing. The boiling point of ethanol is 79, so it evaporates before water does, or I should say at a lower temperature. Okay, and here are the densities of each. So you can see density is a solid. See, look at that. For water here, 0.92 as a solid, and 1.00 grams per cubic centimeter as a liquid. That means that ice is going to float. That's why ice floats on top of the ocean. In other words, so if you took a chunk of gold and you put it in a vat of liquid gold, the chunk of gold would probably float. I don't know. Do we have gold here? Look at this. All right. Here's solid, 19.3. Here's liquid, 17.4. So what that means is the solid gold would go to the bottom as it melts. All right? But not for ice. Ice goes to the top and stays melted. And believe it or not, that's an enormous significance for many, many weather processes and many other erosion processes on the surface of the earth. For instance, out in the Rocky Mountains, where they have abundant snow and ice, the Himalayas, the Appalachian Mountains, any mountain range you want, where there's some snow and ice, the ice will get down into the cracks of the rocks, and it'll freeze, it'll expand, and it'll break the rocks apart. And those rocks will eventually become little tiny pebbles, and then they'll become sand, and then they'll turn into dirt eventually. So anyways, look at these. There's no rhyme or reason to these melting points. Well, I suppose for a chemist maybe there are, but you can see they're just, you just got to measure them. All right? And the same with the boiling points. So silver has a lower melting point than gold. But look at lead. Lead is really low melting point. Still pretty hot. But Davy Crockett can melt lead around the campfire and make new lead shot for his shotgun or for his musket. But melting iron, forget about it. 1538. Copper, the same. You got to have a lot of temperature. Aluminum, look at this. boiling point. And then here's the densities. So I'm just looking at all these metals. The solids are all larger density than. So look at that. Isn't that kind of weird? Water. The one substance on this table, anyways, for which the solid is less dense than the liquid. Everything else is the other way. Now let's go back to this picture here. And I'll just remind you here with this upper note that the energy on the symbolized Q is on the horizontal scale. Temperature in kelvins is on the vertical scale here. So here's a couple concepts that I want to reinforce with you. And that is to melt or to freeze, to boil or to condense, you're basically trying to force the molecules to organize themselves with molecular bonds, or you're trying to disorganize them. A change in the organizational state. So either bonded or loosed. Bonded tightly for a crystalline structure, like water, ice. Bonded loosely for a liquid structure, in other words, water droplets. Enough force to cohere together, cohesively form a droplet, a spherical droplet, but not much more than that. Or completely dispersed and completely obliterated to be in a gas state. So what that really means is that it needs more kinetic energy or less to prevent or to form intermolecular bonds. Now, a couple comments about that on this table. We're going to look over here at this first energy range here, actually the second energy range. Okay, this is a diagram where you have 40 grams of water that's going from 253 Kelvin, that's 20 kelvins below the freezing point, up to 393 Kelvin, that's 20 degrees or 20 kelvins above the melting point. Okay, so you heat it up, and so the temperature rises, and then at 273, you have to either break things apart or put things together. All right? So if you're going in this direction, in other words, if you're trying to melt, go ahead and make a note of that in your diagram. What that means is that you have to add energy. And that means the kinetic energy of those molecules is so big they'd like to, but they can't stay in a good organized crystal lattice. They still have a little bit of neighborliness, but not much. Okay? And so you're adding energy as you melt. And everything is still at 273 Kelvin. So this is ice and liquid water and solid water coexisting at 273. And if your system is well insulated with styrofoam or something, they'll stay that way for quite a long time. Now we have a cooler at home. Sometimes we go on, outings and stuff, and we bring, we don't have everything. We don't consume everything. We don't empty it at the end of the day. And the next day I go and empty it. It's still got a ton of ice inside of it. It's still cold and nice. So good insulation, everything will stay at 273. All right. Now what that means is that Q1 is less than Q2. That's what this chart means. So melting means you're going to the right from a lower value of Q to a higher value of Q. All right. You're adding Q. You're adding heat energy. All right. Whether that's, and you can make a note, you're adding Q from sunlight. You're adding Q from friction, like rubbing your hands together. You're adding Q from a light bulb. You're adding Q from any number of things that you can do to heat things up. Okay, your metabolism, when you break down food, your body's at 98.6 Fahrenheit approximately, and that's your metabolism doing that, and all those chemical processes. Now, the other direction, go ahead and make another arrow to the left. Okay, that's the freezing process. Still at 273 Kelvin, but now you've come in from up here, high energy state, high temperature state, and you've dipped down to 273, and now every time you extract some energy, like a refrigerator, you're going to a lower Q value. You're extracting Q. Okay, you're lowering the Q of your liquid. And when you do that sufficiently, in your ice maker, in your fridge, up on top, or wherever your ice maker is, you get some solid ice. All right? And again, because this time you're going from Q2 to Q1, a lower energy state. And so thinking about the temperature, when the temperature decreases, the average kinetic energy decreases. Right? When the temperature increases, the average kinetic energy of the things you can't see increases. Right? So temperature and kinetic energy average kinetic energy, they're proportional. All right? The temperature is the macroscopic measurement, whether it's with infrared or a thermometer, where the mercury expands a little bit, or whatever they use, you can measure it. It's a single measurement that reflects the average kinetic energy of zillions of molecules. E pluribus unum. And the structure of the substance, the bulk of the substance, we're talking about not just one molecule, but a zillion molecules. The structure will change from crystal to liquid to gas, or the other way. If you extract energy, you'll go from gas to liquid. It'll condense. And then extract more energy, it'll go from liquid to solid. It'll freeze. Okay? And so every substance on this Earth, we just got to measure it. There's different amounts of energy that are required to go from gas to liquid, from liquid to solid, from solid to gas, or vice versa. Sublimation is the process that CO2 undergoes. At normal atmospheric pressure on the surface of Earth, CO2 does not melt. It goes straight to a gas. So solid CO2 down here as a solid doesn't go to a liquid under normal atmospheric pressure. You have to have a little bit higher pressure to do it. It goes straight to a gas. And every substance is different. All right? So if you look at this picture, each solid line corresponds to a certain amount of energy per gram. Okay? So if you have a gram of H2O, it requires a certain amount of energy to go from solid to liquid, from ice to liquid water. But if you have a solid gram of gold, it takes a different amount of energy to melt it and get liquid, melted gold, molten gold. All right? And that is encoded in this table. This is from page 91. Specifically in the latent heat of fusion. This is the amount of energy per gram, calories per gram, that these substances need. You need to add this. You need to add 80 calories per gram for water to melt it. You need to extract 80 calories per gram to go from liquid water to solid water, to freeze it. Okay? Now, ethanol, look at how easy it is to freeze or to melt ethanol. Very easy. 24.9 calories per gram. That's cinchy. But now, copper, 49. Look at gold. Whoa. Gold is super. You got to heat it up. to a high temperature. But then once you get it up there, it's really easy to melt. All right? And lead, easiest of the lot to melt. Now, so make a note to yourself. The latent heat of fusion, you're thinking gram for gram. Okay? Gram for gram, it takes a lot of energy to melt ice. Gram for gram, it takes a fairly small amount to melt lead. Now, a gram of lead is a different size nugget than a gram of ice, because they're different substances. A gram of lead is a pretty small little nugget, but a gram of ice is going to be quite a bit bigger. All right? Same thing for the other phase transition from liquid to vapor. Okay? So look at this, 539 calories to vaporize a gram of water. Holy buckets. Look at that. To turn a gram of water into a gram of ice into liquid water, 80 calories. To take that same gram of liquid water and turn it into water vapor, bing, 539. A lot of energy. But once you've done that, it's completely disorganized. It's chaotic. It's unorganized. It's a gas. All right? Same thing for everything else. Let's look at lead down here. Whoa. Whoa, look at copper. Ooh, copper's tough to vaporize. Over twice as hard to vaporize as, gram for gram anyways, as water. Question?
So the higher the number, the harder it is?
Yeah.
Okay. So
Yeah.
like,
So once you get it up to the melting point, or once you get it up to the boiling point in this last column, then this is the number of grams that you have to add to break it apart from a solid into a liquid. Or in this column, from a liquid into a completely dissociated gas. Okay? So it's... And I always like to think of the latent heat of fusion as the amount of energy to bust up those crystalline bonds. So think of it as just, tearing your way through a pizza. To consume a pizza, it takes work. The same thing here. You got to break up all the bonds of ice, the intermolecular bonds. It takes 80 calories to break them all. In a gram of water ice. Okay, so here's a kind of a summary, vocabulary terms. Liquid to solid, that's freezing or solidifying. We usually use the word freezing for water and, ethanol and stuff like that. We don't really use the word freezing for gold. We use solidify. But you could use the word freezing if you want. Liquid to gaseous state we call it boiling or vaporizing. Solid to gaseous, as I mentioned before, sublimation. And that's harder to observe for most things. CO2, though, you can see it. That's why CO2 is called dry ice, by the way. And solid to liquid is called melting. Gaseous to liquid is called condensation. That's how we get water vapor turns to liquid droplets in the condensation process, and that's how we get raindrops. Gaseous to solid, that is something that they do in labs. It's called deposition or epitaxy. So the gaseous is usually the higher energy state, and the solid is the lower energy state. And then, of course, the ambient pressure affects all of these transitions. So if you read, I'm not going to go through the properties of CO2 on exam 2, but if you feel like reading about CO2 and its phase transitions, you can sure do that. Now, so ambient pressure affects the transitions as well. So dry ice. That's my comment about dry ice. Now we're going to cover the dry ice situation next week. You can read ahead if you want. Before we dismiss, I'm not dismissing yet. Okay, she's not going to know anything about exam 2. Okay, the answer to number 7 is. Ooh, the room went quiet. No. So you're going to have a couple homework assignments. Now, exam 2. Make sure that you know stopping time problems, stopping distance problems, the different variations of stopping time. You know, figure out the stopping force from the stopping time. Stopping distance, the different variations of that. Make sure you know that your definitions of kinetic energy, potential energy, and momentum. Pressure that we talked about. Gravitation. And don't forget, you are still obligated to remember F equals ma and centripetal acceleration and everything from exam 1. So I say it's lecture 9 through lecture 15. Is this lecture 15? Yeah. But it actually goes all the way back to the beginning because we're still talking about F equals ma. All right? Expect to have some 2 or 3 calculations at various levels of difficulty. Now, I've been having trouble with the clickers, so I'm planning to have clicker problems running for the exam. All right? So that means you've got to bring your iClicker. Do not be a slacker. Do not let your iClicker escape. And be ready to handle calculations and type in the numbers, just like we did last time. If you want to be an SSG leader, you want to crush this test. And as I've said many times before, find a study partner. Or go to SI and find a study partner. Okay, you're dismissed. I'll see you on Thursday.